Observe this network. Each node here represents a service, a server, or a critical component of a distributed system. Some nodes fail, some slow down, and yet the system continues to operate seamlessly. How is that possible? In modern distributed systems, resilience and security strategies ensure that even under failures, overloads, or attacks, systems remain operational, reliable, and secure. Today, in the final video of this series, we'll explore the advanced patterns and practices that make this possible. So why does resilience and security matter? It's because failures are inevitable. Servers may crash unexpectedly, microservices become slow or unresponsive, networks may partition or drop messages. Without proper design, these failures cascade, causing downtime, lost transactions, and a poor user experience. Resilience ensures systems continue to function despite failures, while security ensures that data and users remain protected. To achieve robustness, distributed systems employ proven patterns. Circuit breaker functions like an electrical fuse. Repeated failures trigger an open circuit, stopping further requests temporarily. Prevents cascading failures across services. Example, if a notification service fails repeatedly, requests fail fast, allowing the rest of the system to operate normally. Second, bulkhead. It is inspired by compartments in a ship. Isolate resources so failures in one part does not affect others. Example, a separate thread pool for payment processing and reporting prevents spike in reporting from blocking payments. Third is the saga pattern. It manages distributed transactions without a single global transaction. Each step is a local transaction. Failures trigger compensating. Example, booking a trip across flights, hotels, and cars. If a hotel booking fails, the flight and car reservations are rolled back automatically. CQRS, Command Query Responsibility Segregation. It separates write operations, which are commands, from read operations queries. It optimizes for performance and scalability and supports event-driven architectures and eventual consistency. Event sourcing. It stores a log of all events, not just the current state. It enables auditing, replay, and reconstruction of a system state. Example can be that each payment attempt is an event. The current balance is derived by replaying all events. Even resilient systems require protection. Authentication and authorization. It ensures that only valid users or services can access resources. Example, OAuth tokens for API requests. Rate limiting. It controls request frequency to prevent overload or abuse. Example, limiting login attempts to prevent brute force attacks. Failover mechanisms. Automatically switches to backup services when primary fails. It guarantees high availability and continuity of the service. Monitoring and alerts. It tracks health metrics, logs, and performance, triggering alerts for issues. An example can be spike in payment service latency triggers rerouting to healthy instances and alerts engineers. So how patterns and security work together? Advanced patterns and security measures complement each other. Circuit breakers prevent failures from cascading. Bulkheads isolate critical resources. Sagas maintain consistency across distributed services. CQRS and event sourcing provide scalability and traceability. Authentication, rate limiting, failover, and monitoring protect users and maintain availability. So let's see what a banking transaction may involve. It may involve Saga for transaction coordination, circuit breaker to stop repeated failures, bulkhead to isolate payment processing threats, event sourcing for auditing, monitoring, and alerts to detect resolve issues. Even in complex failure scenarios, the system continues operating safely. Now let's reflect on the series as a whole. Consistency and consensus. How replicas maintain correctness using Paxos, Raft, and Quorum systems. Performance and load balancing. Efficient traffic distribution, latency optimization, and scaling with layer 4 and 7 balancing. CDN and edge computing. Microservice and SOA. Modular independent services with service discovery, API gateways, and communication patterns. Resilience and security. Patterns and practices that ensure systems survive failures, maintain integrity, and protect users. By integrating these concepts, you can design distributed databases that are reliable, scalable, and secure in real-world environments. This concludes our series on distributed systems today. Today, we have explored advanced reliance patterns, security measures, and strategies that ensure modern systems continue functioning reliably even under failures and high load. You now have a comprehensive understanding of how distributed systems maintain consistency, how they handle traffic efficiently, optimize performance, and how modular microservices support scalability and maintainability, how resilience and security patterns protect users and maintain availability. These principles form the foundation of modern large-scale systems, and we encourage you to apply these patterns thoughtfully, continue exploring the field, and build systems that are not only functional but also robust and secure. Thank you for watching this series, and we hope that it has provided valuable insights to guide your journey in designing distributed systems.